All right, so get ready for this. Okay. Today, we're doing something a little bit different. We're actually going to be opening up a physics textbook.
A textbook?
Yeah, not just any textbook, though. We're diving deep into the physics textbook for Standard 9X, so that's ninth grade, straight from the Government of Kerala Department of Education in India, published this year.
Wow. That's pretty interesting. It's a great way to see how physics is being taught, halfway across the world.
Yeah.
And what we can learn from their approach.
Exactly. And trust me, there is some really cool stuff in here.
Oh, I bet.
We're talking optical illusions, the physics behind catching a cricket ball.
Wow.
Even a peek into black holes.
Really?
Yeah. By the end of this deep dive, you'll be like dropping physics knowledge like it's nothing. You'll be like, oh yeah, I know all about that.
I'm excited.
Me too.
Yeah.
Okay, so first things first. The book starts with the Indian Pledge and National Anthem.
Okay.
It really highlights how important national identity is within their educational context.
That's a really interesting observation, and it kind of makes you think about the subtle ways that cultural values are woven into education.
Absolutely.
Right.
And the preface emphasizes their goal of helping students understand and apply physics, like in everyday life. They're not just like teaching formulas.
Yeah.
They're showing how physics is all around us.
Yeah, I like that a lot.
Yeah.
Speaking of everyday life, they jump right in with a question I'm sure we've all wondered at some point. Why does a straw in lemonade look bent?
Oh, I remember being like totally baffled by that as a kid.
Right.
It's like, just magically bends at the surface of the water.
So the textbook explains that, it all comes down to refraction, light bending as it passes between different mediums, So in this case, the light from the straw is traveling from the water or, lemonade in this case, into the air. And that change in the medium causes it to bend.
Okay, so the light bends, but like why?
So, light actually travels at different speeds depending on what it's moving through. It moves super fast through air.
Right.
But it slows down when it hits denser materials like water or glass.
Okay, so the light from the straw is like slowing down as it leaves the lemonade and enters the air.
Exactly. And that difference in speed causes the light to change direction, giving us that bent straw illusion. And the textbook actually includes a really cool table showing the speed of light in all these different mediums.
Oh, wow.
And it really helps to kind of drive this point home.
That's so cool. And they don't stop at just the bent straw, right?
No.
They use refraction to explain why the bottom of a pond appears higher than it actually is.
Right.
And why bow fishermen aim below the fish they're trying to spear.
Yeah, and get this, refraction even explains why stars twinkle.
Oh.
It's the light from those distant stars passing through, all these different layers of our atmosphere, each with a slightly different density.
Yeah.
And that's what causes that twinkling effect.
Wait, so it's not the stars themselves that are twinkling? It's like our atmosphere is messing with the light.
Exactly. It's kind of trippy when you think about it. And because of refraction, we can actually see the sun for a few minutes, even after it's set below the horizon.
Oh, really?
Yeah.
Pretty cool, huh? Wow, that's mind-blowing. I never realized, how much physics was packed into these, everyday things that we see all the time.
It's amazing. And the textbook keeps going, seamlessly transitioning into motion. They set the scene with these kids, right? Watching a train cross a bridge.
Okay.
Wondering, how do you even figure out how long it takes?
That's such a clever way to introduce the idea of, calculating time, distance, and speed.
Yeah, exactly. And it also helps them kind of introduce the difference between, distance and displacement.
Okay.
Distance is simply how far something travels.
Right.
While displacement considers the direction, a final position relative to the starting point.
So, if you walk 10 meters forward and then 10 meters back to where you started, your distance traveled is 20 meters.
Right.
But your displacement is 0.
You got it. And that distinction is super important in physics.
Okay.
From there, they delve into, uniform versus non-uniform velocity.
Okay.
Using examples like a stone falling from a height,
right,
light traveling through a vacuum, and a bus starting and stopping.
Okay, yeah. I remember learning about velocity in school.
Yeah.
It's basically speed with a direction, right?
Exactly. And this leads naturally into the concept of acceleration, which they illustrate with the example of a bus, speeding up.
Okay, so acceleration is how quickly something changes its velocity.
Exactly. And they go on to define, uniform and non-uniform acceleration.
Okay.
And this is where it gets really interesting. They don't just talk about these concepts in a vacuum,
Right.
They connect them to something super practical, road safety.
I love that.
Yeah.
They're showing how physics can actually save lives.
Exactly. They talk about the importance of traffic rules for both pedestrians and drivers, and break down all these different types of road signs. Mandatory, cautionary, informatory.
Right.
Giving specific examples from Indian Road.
Yeah. It's a great reminder that, these signs are based on physics principles.
Absolutely. They even talk about why wearing light-colored clothes at night is so important. It's all about making sure drivers can see you, which ties directly back to the physics of motion and reaction time.
Right. It's like they're saying, hey, this physics stuff isn't just theoretical. It can actually keep you safe out there on the roads.
Exactly. And speaking of important physics, the textbook then dives into one of the most fundamental concepts.
Okay.
Newton's laws of motion. And they start with a really classic scenario. A tug of war. A simple but effective way to introduce the idea of force, balanced forces, and unbalanced forces.
I can already picture that, like tug of war in my head. It's a great way to show how forces can either, work together or against each other.
Absolutely. And then they guide the reader through this really cool experiment using a toy car and pans with weights.
Okay.
It's a really hands-on way to demonstrate the relationship between force, motion, and acceleration.
I bet that experiment would be a lot of fun to try at home.
It would be, but before they just drop Newton's laws on us, they take us back in time to Galileo and his experiments with marbles rolling down inclined planes. It's a great way to show how scientific knowledge builds upon the work of those who came before.
It's like a little history lesson woven into the physics,
Exactly. And then they finally introduce Newton's first law of motion, that whole an object at rest stays at rest and an object in motion stays in motion thing.
I remember that one. It's all about inertia, right?
Yes. You got it.
Okay.
And then they do such a good job of explaining inertia with relatable examples, like why passengers in a bus jerk backward when the bus suddenly starts moving.
Yeah.
Or, why shaking a mango tree makes the mangoes fall down.
Okay, those make sense. So inertia is basically an object's resistance to changes in its motion, right?
Exactly. And the textbook goes on to explain how mass affects inertia. Yep. The more massive an object is, the harder it is to get it moving or to stop it once it's already in motion.
Right.
And they describe an experiment using bottles filled with sand to kind of illustrate this. How much harder it is to move a bottle that has more sand in it.
That's a great visual.
Yeah.
I can totally see how that works.
Yeah. And then they touch upon the concept of momentum.
Right.
Which is basically like how much oomph a moving object has.
Right. Like a bowling ball has more momentum than a tennis ball.
Exactly.
Even if they're both moving at the same speed.
Exactly. Momentum is influenced by both mass and velocity.
Right.
So a heavier object moving fast has a lot of momentum.
This is all starting to come back to me from my high school physics days.
It's amazing how it's all connected.
It is.
Isn't it? And speaking of connections, I think maybe we should pause here for a second.
Okay, and let all of this sink in before we jump into Newton's other laws and all the other fascinating insights from this textbook.
Sounds good. We'll be right back to continue our deep dive into the world of Indian physics. Okay, so welcome back. We're continuing our journey through this Indian physics textbook. Before we took a break, we were exploring Newton's first law of motion and the whole idea of inertia.
Right, and building on those ideas, the textbook moves on to Newton's second law.
Okay.
Which introduces this, really important equation, EVMA.
Yes. Force equals mass times acceleration. That one definitely brings back memories.
Yeah, it's a foundational equation that helps us understand how, forces and mass and acceleration are all related.
So it's not just a theoretical formula, right? It's a tool for solving problems.
Exactly. And they give some really cool examples, to illustrate how it works in different scenarios.
Okay, like what? What kind of examples? Well, they talk about, how you could use the equation to calculate, the force needed to accelerate a car at a certain rate, or to figure out, how much a rocket would accelerate given a specific thrust force.
That's really cool. It makes the whole concept, more real.
Right. And then they go on to introduce two more concepts, impulsive force and impulsive force.
Okay, I'm listening. What are those all about?
Well, so impulsive force is a large force that acts over a very, very short period of time. Think about, hitting a golf ball or a tennis ball, that sudden impact. That's impulsive force.
Okay, got it. So the impulse of force is?
It's simply, the force multiplied by the time interval over which it acts.
Okay.
But here's the really cool part. The textbook explains that the impulse of force is actually equal to the change in momentum of the object. They call this the impulse momentum principle.
So when you hit that tennis ball, you're not just like applying a force, you're actually changing its momentum.
Precisely. And they connect this principle to some really interesting real-world situations, like catching a cricket ball.
Oh, that's interesting. How does that work?
So when a fielder catches a fast-moving cricket ball, right, they move their hands backwards along with the ball as they catch it.
Okay, I've seen fielders do that. Why do they do that?
So by increasing the time over which the force is applied, right, they're actually reducing the impact force on their hands.
Oh, so it's a way of making catching those super fastballs less painful.
Exactly. It's all about managing those forces and momentum. It's the same principle that goalkeepers use in football, right? When they're trying to catch a really powerful shot, they try to cushion the ball to increase the impact time.
Wow, that makes so much sense. So it's like physics is behind so many sports techniques.
Absolutely. And the textbook seamlessly goes from the impulse momentum principle to Newton's third law of motion.
Okay.
For every action, there's an equal and opposite reaction.
I remember that one. That one always makes me think of like two ice skaters pushing off of each other. They both go backwards, even though they're applying force in opposite directions.
That's a perfect example. The textbook uses some fun experiments to illustrate this law, like, a balloon attached to a straw threaded through a string.
Right.
When the air rushes out of the balloon, it propels the balloon itself in the opposite direction.
Like a mini rocket.
Exactly. They also describe this experiment using two spring scales hooked together. When you pull on one scale, both scales show the same reading, just in opposite directions.
Okay.
It's a very simple but effective way to demonstrate that forces always come in pairs.
So for every force we apply, there's always an equal and opposite force pushing back.
Yes, exactly. And they give some really great real-world examples of this law in action, like rowing a boat or even like, jumping off a boat onto a dock.
I bet that makes the boat go backwards.
Exactly. It's all about those action-reaction pairs. So we've covered a lot of ground, with motion and forces.
Yeah, we have. It's amazing how much physics is behind like these everyday actions and movements that we make.
It is. It really is. So what's next on this journey through the textbook? Well, they go on to tackle another fundamental force, gravity.
Oh, gravity. That one's always like a head scratcher for me.
Right. So they start with this simple observation that we all know. Objects fall to the ground.
Yeah, true. What goes up must come down, right?
Exactly. So from there, they introduce gravity as a force of attraction between objects. Explaining how it depends on mass and distance.
So the more massive an object, the stronger its gravitational pull. And the farther away two objects are, the weaker the force between them.
Exactly. And they don't just talk about us being pulled down to Earth. They bring in Newton's law of universal gravitation.
Okay.
Which states that every object in the universe attracts every other object.
So it's not just about Earth's gravity. It's a universal phenomenon.
Exactly. They connect this to tides, explaining how the gravitational pull of the moon and the sun cause the rise and fall of ocean levels.
That's such a cool example. It really makes the force of gravity, like, less abstract.
It does. And they even provide this table, showing how gravitational force changes as you move farther from Earth's surface. The farther away you get, the weaker the pull. And they even go on to introduce this concept of the gravitational constant G.
Oh.
It's this fundamental constant in physics, and it helps determine the strength of that gravitational force. And it's the same value everywhere in the universe.
So no matter where you go,
Yeah.
that force of gravity is going to be acting on you.
That's right. And you know what else? They introduced this idea of acceleration due to gravity, G.
Right.
Which is basically, how quickly an object accelerates toward the ground because of gravity. The really interesting thing here is that G is actually independent of the object's mass.
Wait, so a feather and a bowling ball would fall at the same rate if there was no air resistance?
Exactly. It seems totally counterintuitive, right?
Yeah.
But the textbook describes this classic experiment where they drop a feather and a coin in a vacuum tube. And, with no air to slow the feather down, they both reach the bottom at exactly the same time.
Oh, wow. I'd love to see that experiment for myself.
Yeah, it's really cool. And, they don't shy away from some of the complexities of gravity either. Like, they talk about how G actually varies slightly depending on where you are on Earth. It's slightly stronger at the poles than at the equator. And they even touch on this, mind-bending concept of black holes.
Black holes. Okay, now we're talking. Those are regions of super strong gravity, right?
Exactly. They're so dense that not even light can escape.
Whoa. Okay, so We've gone from bent straws to black holes in just a couple of chapters.
It really is amazing how this textbook just, like, seamlessly connects everyday things, with the most extreme objects in the universe.
It is. It really shows how physics is, like, everywhere.
Yeah.
From the smallest particles to the largest structures.
It is.
But before we get too lost in space, maybe we should pause here for a moment and let all of this amazing information sink in.
Sounds good to me.
And we're back, ready to wrap up our exploration of this Indian physics textbook.
I am. Before the break, we were talking about gravity and even black holes.
I know. It's mind-blowing.
And now, the textbook goes on to address this really common misconception about the difference between mass and weight.
Oh, yeah. I definitely remember, getting those confused.
Right. So many people do. But the textbook emphasizes that, mass is a measure of how much matter an object contains, while weight, on the other hand, is a measure of the force of gravity acting on that mass.
So your mass would stay the same, no matter where you were in the universe.
Right.
But your weight would change depending on the gravitational pull of the planet or, moon you're on.
Precisely. They give a great example about, imagine taking a 10-kilogram object to the moon. Its mass would still be 10 kilograms, but its weight would be much less because the moon's gravity is weaker than Earth's.
Okay. Yeah, that makes sense.
Yeah.
So mass is more about, the inherent property of the object.
Yeah.
And weight is about the force acting upon it.
Exactly. And from there, they kind of introduce these concepts of free fall and weightlessness.
Okay, I'm intrigued. Tell me more about that.
Well, so think about, what it feels like when you're in free fall, like skydiving or being on a roller coaster that suddenly drops.
Yeah, like that feeling in your stomach.
Exactly. You feel weightless,
Yeah.
even though obviously gravity is still pulling you down.
Right. So, why do we feel weightless if gravity's still acting on us?
Well, it's because you're accelerating towards the ground at the same rate as everything around you. The textbook describes this really cool experiment. Imagine dropping a mass attached to a spring balance. As the mass falls, the reading on the balance drops to 0, even though the mass itself hasn't changed.
Whoa, that's so weird. It's like gravity is temporarily, switched off.
Right. It's all about relative motion and acceleration.
Yeah.
So from free fall, they move pretty smoothly into another type of motion.
Circular motion.
Oh, circular motion, like a Ferris wheel. Yes,
There.
exactly. Or those spinning carnival rides. Perfect examples. The textbook uses a simple illustration of whirling a stone on a string. The stone's moving in a circle at a constant speed.
Okay, but even though the speed is constant, it's constantly changing direction.
Exactly. And that constant change in direction means that, there's acceleration involved. And the force responsible for keeping that stone moving in a circle, it's called the centripetal force.
So in that case, the centripetal force is the tension in the string, pulling the stone inwards, keeping it from just flying off in a straight line.
Precisely. And they go on to connect this concept to the motion of planets and satellites, pointing out that Earth's gravity is acting as the centripetal force for satellites orbiting our planet.
It's crazy to think that, the same force that makes an apple fall from a tree is also responsible for keeping satellites in orbit.
It is. It's pretty amazing. And speaking of satellites, the textbook even highlights Chandrayaan-3.
Oh, yeah. India's mission to the moon.
Exactly. Which was a huge accomplishment. And you know what they point out? To achieve that soft landing, the spacecraft had to overcome the gravitational forces of both Earth and the moon.
Wow. It's really cool how they bring in these examples that are, so relevant to Indian students.
Absolutely. It's a great way to show how physics is not just theoretical, but it plays a key role in, all these scientific advancements.
It does. So that brings us to the end of our deep dive into this Kerala physics textbook.
Wow.
What a journey it's been. We've covered so much, from refraction and motion to gravity and black holes.
Yeah.
And I really love how this textbook takes these kind of abstract ideas and makes them relatable through everyday experiences.
Me too. It makes you realize that there's so many different ways to teach and learn about this subject.
Exactly. It
Yeah.
just goes to show that there's, always more to explore and discover in the world of physics.
Absolutely.
Well, thanks for joining us today on this fascinating adventure. Who knows, maybe you'll be inspired to check out this Kerala physics textbook yourself and see what other insights you can find.
I know I am.